Okay, before the break, we were working our way through a little bit more, a couple more points on our example. What we did was we threw in some little red knight to counter our dragon player character to be an enemy, and we started looking at what it took to move him around. This was just a quickly thrown together example. Should be walking in a box there, but there's variants. The main point of it is that we have to script the whole thing out. We can't wait for the user to make a decision and then push key press. For the computer control characters, we have to give some sort of control. And the math here should be walking in a straight box, but when we run that, you'll notice our character doesn't really get back to the beginning. We're walking, I'll say forward for a certain amount of time, then we go to the right for a certain amount of time, back, and then to the left, and the time should line up, but our character ends up someplace different. And remember, there's other things that come into play here as well. So in particular, if he's not walking on perfectly level ground, after that movement from our script, the character is going to, gravity will take in and pull the character slightly down the hill. Or if we're in a frame where there's slight uphill or something. So there's lots and lots of little adjustments that will need made if you want a particular path like that. But it gets some sort of starting point. And we are very restricted in class, so we can't spend a whole lot of time working with it. But that should give you a pretty good idea on how to deal with the starting points there. And the basic idea is that we have to basically determine the entire path. We went off the frame number here, but we use position as well. If you're on uneven ground, position might work better for a distance. And go 20 meters one direction, then 10 meters over, 20 meters back, and 10 meters over again. Yeah.
Could you say keep going until your X and Z positions are this, and
yes,
so it will always be
yes.
exact.
And we have our transform that. Actually, we've already grabbed that. All we need to check is if current X is equal to that specific thing. There's different ways, and every game is going to be unique, so you'll want to play around with it. But the main thing is we have this selection structure that's going to keep us walking, keep us doing something. But I'd skipped over the if part because we really only want to follow that condition unless we're entering a game state. Like the dragon is close enough to we want the red knight to start attacking the dragon, to start chasing him down. And to find that, we need to use the Pythagorean theorem. The Pythagorean theorem also works in 3 dimensions, so if there's elevation involved, instead of a squared plus b squared equals c squared, we just have another number in there, a squared plus b squared plus c squared equals d squared, so that straight line through 3-dimensional space off at some weird angle that's not on a flat plane. And really, it's probably only 2 or 3 that are going to show up on the game ones, but the Pythagorean theorem applies to any number of dimensions. We just keep adding things on that sum of squares, and that equals the straight line distance squared. So what we need to find is the distance to the player. So we'll use the Pythagorean theorem, but first thing I have to do is get the zoom buttons out of my way, because they're not disappearing. Oh, there you go. But look at the chat room and then close it. It'll the buttons will start disappearing again. So first thing we need is a way to know where both our character and the red knight are. So over here in our script, we have the character, we have the red knight's position, and the same way we set speed, we can just grab a reference to the other thing. So, public, and I'm just gonna go with game object data. And then we can just assign it to that dragon game object and then pull the transform out of that to get to the position. I'll call it dragon. That way we can know where it is. Again, lots of different ways. So we're just kind of looking at a sampling here. Takes many years to try all the different alternative ways to put these things together. We're just looking at a sampling to get started. So that gives us a spot to refer to the dragon. And it's good form that as soon as we do something like that, it's a good idea to come over and make that assignment. Oh. Which is not gonna let me do that with that line only halfway type. I'm gonna comment out that line or started putting the distance away. And, yeah. Just to avoid forgetting it, whenever we set up those public fields, it's a good idea to come over and assign them directly. And we usually do the drag and drop. So if I go to assets or scene, you can see there's a lot of stuff in this scene. Our dragon's animated, so we don't just have the dragon, we have all the bones and the armature of the dragon. Data, not just game object. There it is down on the list, but you can see how the list of things we can select from is a lot longer than just the list of game objects we have. But it's usually better to do the click and drag method. And we'll get a reference to our dragon object. So then I'll split this up amongst several lines to make it a little bit easier to work with. Is our player also has transform data that we can access. And we already have our current one. So then we just need the other one to find the distance between them. So below the player X is going to be that dragon object, which is a game object. And from a game object, we can grab a transform data. And transform data has position data as part of it. And then that has an X position. There's an X position. I'll leave it there on the screen for a second. You can see how it's very similar to the previous stuff. But when we were doing our own transform, it was implied what the object was. So we're able to leave that part off. But now we have to specifically say which object we want. And in a big complex game, there's going to be lots of other objects we want to take the distance to, not just that one. Which would be another one related to your question a moment ago, Dylan. Another thing we might want to check, well, especially when we get to the NPC in a few minutes and do random movement instead of a pattern, is check the distance to the edge of the world so we don't fall off. But there's often a lot of things that we need to check. Then I'll duplicate that line twice and just change this X to Y and this one to a Z. And we've talked about it before. Remember, it's not intuitive since we're all native English speakers, but it is more productive to work up and down the columns than it is to work across. Especially if we have something like this where all three of those lines are very, very simple. So, whoops. Now, both of our positions are coming in floating point data. So if we start doing math with floating point numbers, we know we're going to get back to floating point number. Okay. That's just a basic concept for math. We work with integers, we usually get back an integer until we start dividing. If we work with floating point numbers, we're going to get back floating point numbers. And Can't remember if we've used it yet or not. It probably should have showed up in that example when we did the C# syntax. But there's a library called math that has a lot of the math functions you're probably used to and would expect, right? Absolute value, square root, different things with angles, radians, degrees, and all our trig functions, sine, cosine, and the rest of them. And all of those, and in particular, the math library is for floating point numbers. There's more than one math library, basically. For those who have only seen a lot of Python before this class, or only seen stuff in Python before this class, Python kind of spoils people because there's only one math. Usually we have multiple math libraries, and we want to pick and choose between them. But we're working with floating point data, so we want math. And generally, even if you're working with integers, for Unity, most people just still go ahead and use math. It's less to remember every time. And it's the one that has the most, the F probably doesn't stand for float, but at least that's what I think of as floating point number. But math F is the one we can use. And it's a lowercase f, so that's why I'm pretty sure it stands for floating point number. If it stood for something, it would be a capital F for camel case, or that other part would be spelled out. So I think it's just like when we have floating, like if we want 3.14 as a floating point number instead of a double, we have to type that F at the end. So math library has a square root function. So from the Pythagorean theorem, C is the square root of a squared plus b squared. And we only want the distance between them. We can get back to that picture on the board. Stop screen. So if we have our two things and there's some line going between them, what we really care about for finding that distance is the X and Y components, but it's not based off the origin. So we can't use just this X value. We just want to find the difference between them. So like to get from here to here, X1, Y1, X2, Y2. We just need the difference between those X values. Oh wait, this would still be Y1. So this is the X value from that one, and the Y value from that one gets us down to the corner of the triangle here. Because over here, X1, Y1, and then up here we have X2, Y2. And really what we need is to find the difference of them to find out how long that is. So here, X1 minus X2 tells us the difference between them. It could be negative, right? Is that a concern for us? If we start to plug it into the Pythagorean theorem, what's the first thing we're going to do with that number? Square it, right? And square numbers are always positive. And the negative times the negative cancels out. So that's one thing you might want to stop. I think you need to stop and worry about order, but the order won't matter. First thing we're going to do is square that number. So that's like our a squared plus the y's. Y1 minus Y2. Then when we square it, and then to switch it to the Pythagorean theorem, we need the square root of all of And that gives us our distance. I'll just write D on the board. So we have to know both points, and then the difference between those 2 points is the value we actually want. And luckily the Pythagorean theorem squares everything, so we don't have to worry about positive or negative. If you end up in a situation where you do have to worry about positive or negative, think through which one is positive or negative, or take the absolute values or something like that. Basically, it's going to look almost like right on the board, except I use the regular square root symbol instead of dot square, like we put in programming. But our, I'll do player first. Player X minus our current X. And since it's just squared, I'm just going to multiply it out. To do exponents, we should really be using a pre-built function. But for squaring, I find it's a lot easier just to copy and paste that twice. Because when we multiply it twice, so it'll come out the same, and then we don't have to remember some fancy name for a pre-built function. I think our copy and paste stuff from earlier is done. Let me switch this. Zoom buttons are in the way. This one here. There we go. That way this line will kind of fit on, this equation will fit closer to one line. It's still going to scroll over. But then we need that again for our y's. So player y minus current y. Oh, wait, it's not y we need, is it? Double check. I'm in the habit of writing x and y for math class, but y is our vertical direction in unity. And we don't care about elevation here. We just want to know the horizontal, kind of the horizontal distance to it. Because there's lots of different elevations in our world. And both our character and the enemy are perfectly capable of walking up a hill. So we need the z. And that is something you'll want to pay close attention to every single time. Player z minus current z. So that gives us a distance where we can check at what point we should be chasing the character. Or that tells us how close we are to that. And then we can use that to see if we're within a certain threshold. Or what that threshold is going to be. So I'm just going to put it on the interface. Once I find it, or change around on the interface, and then once I find it, you can change that back to private, because it's not one that we necessarily need to have accessible. But it's a whole lot easier if we make it public first. Floating point number, and I'll call it threshold. I'll call it distance threshold. So if our distance player is less than the distance threshold, and instead of just writing threshold, I'm going to spell that out, because typically there's going to be a lot more going on in the game, right? There's going to be several distance thresholds we need to pay attention to, not just one. So we'll end up with big, long, approaching those SA link variable names to keep them straight. And then we can do our primary thing we want our enemy movement to do. And that's if, oh, already have it. If distance to player is less than our distance threshold, then we want to move towards the player. We want to specifically move in that direction. And seeing hands come off the keyboard now, so I'm gonna stop the screen share and go back here. After that, we'll go back to our picture of the right triangle. What is the direction to the carrot? It's here, it's to the left and up. It could be anything in our game, right? It could be down and to the right or any place else on there. But there's some X value and some Y value that we want to move it. So we need that number, but we need to scale it down so we don't move too fast. Okay, so maybe this is, we find that it's 3 in the X direction. But that's going to be, that's going to give us an uneven thing. If we multiply 3 by our speed, we're going to move really, really quick in that direction, right? If we do put the same thing in Y, then we'll move really quick in 2 different directions at once. So what we need to do is scale that down. And most of y'all probably haven't had a math class where you've seen this. So I'll just say this. This is what the word normalize means. I know for certain you've heard the word normalize in programming classes, just not in math classes. So to normalize that, what we have to do is divide by our distance. There's a dot normalize that we could use at the end of the vector. So we put in our new vector and then say dot normalize it. But it spreads out to extra steps. What it really does is it just makes sure everything is smaller than 1. Right. This is our biggest number. From elementary school, the hypotenuse is the longest side of the right triangle. So we know that whatever our side is, so we have our y2 minus y1, whatever length that is, if we divide it by the hypotenuse, we have a number smaller than 1. And that gives us sort of a general direction to point in, kind of like what those key presses did. When we first push the D key, it starts at 0 and then it quickly accelerates up to 1. And that's our max value. Same thing with all our other keys. It gives us some value between 0 and 1. X2 minus X1, again, divided by that distance gives us that value between 0 and 1. And then we can multiply that by our speed, and our character will move consistently in that direction. Has anybody had a trigonometry class? Okay, I'm seeing some yeses. So then obviously, I'm skipping over the then multiply by the sine or cosine. It'll be close enough for today's example. But if you've had trigonometry, you know there's another step there. Figure out whether you're horizontal or vertical and use that appropriately. But we're dealing with small numbers, so it shouldn't be too drastic. But not everybody's had a trigonometry class, so that's going to get really confusing if I throw that other step in there. We get some nice small numbers, so it's kind of like pressing 2 of our keys at once. Okay, so this one's like pressing the D key, and this one's like pressing the W key. So when we press them both at once, we get some small numbers that give us values to go in both directions simultaneously. Well, not simultaneously. The next instruction in the code, right? So it happens sequentially, but it happens so fast that to a human, we call it the same. We're talking fractions of a nanosecond to get to the next line of code and have both movements run in there. And before the graphics move on the screen, both equations will have run. So I guess that's the synchronous part. Right? All the equations run before we move our graphics, and the player only sees the graphics. So go back to sharing the screen. So that's the hypotenuse of our triangle. So then we need, so we're in that distance, we need to figure out what that direction is as a ratio of these two numbers. How much do we move in the X versus how much do we move in the Y, and keep it moving in that direction. I'm gonna leave it like that there. And for those who have had trigonometry, the next step should be obvious, right? I saw some heads nod yes, so where we would apply cosine and sine should be fairly obvious, right? So this is actually gonna move a little bit faster. When we get really close, it's gonna slow down, but we might need to make some adjustments. This will give us a starting point and kind of give the basic idea. And the main idea is use a right triangle, figure out which direction you need to go. And then we can normalize it afterwards. So our move, we'll need a couple more floating point numbers. I'll say move X is going to be that distance between those, current X, divided by the distance to our player. That way it's like our key press. We know we have a number somewhere between 0 and 1, so we don't suddenly shoot off the screen because we're going too fast. But this one could be a positive or negative number. So in this case, we will need to try and do math absolute value of those things. Again, the math F library, and then the standard that you've probably seen in multiple languages by this point. ABS is your absolute value. Oh, wait. And those should both be X's. This line should have all X's in it. And then we'll duplicate that and have one that's all Z's. And then we can create our actual movement vector. So vector 3 data, we'll call it movement. It's a new vector 3. So will be our current X plus move X times speed. I'm gonna leave out a space there to hopefully help show those go together. So just like move X is taking the place of our key press from the controlled movement or player controlled movement. It gives us a number somewhere between 0 and 1, and then we multiply that by our speed to know how much we're actually moving in that direction. Our current Y stays the same because we're not jumping or anything. And our current Z is going to be that plus move Z times speed. And actually, I changed my mind halfway through what I was doing. We don't need the absolute value here, do we? Because then if we need to go in the negative direction, it'll just automatically be negative. I was going to do something else and then changed my mind halfway through it. Y'all know how that goes with coding, right? We think we have an idea and we start typing and it's like, oh wait, I have a better idea before we even finish what we're typing. So I'm going to take that off so that that will also give us the positive or negative value. Make sure you're following the right order for the positive or negative value. That is a delta, just a measurement of change, and change is always the end minus the beginning. So the movement, we want our movement to end where the player's at and start where we are at. So you want to make sure you go player minus our own movement, player minus our own position in that order, end minus beginning, and sometimes we have to twist the words around to make sure we have the right order. But that should give us the correct negative or positive value. Then we have how much we want to move, and then we just go like we saw before. We can just reset our transform to that new position. It is reassign that movement. Everything makes sense there. See how it's a lot more of what we did before. The only difference is it's, we have to spell it all out. We don't have a human making decisions along the way. So we go back over to Unity. Oh. QRT. It should. Unless I forgot to import something.
I think it's
Capital F.
capital S.
Oh, yes. That's right. In C sharp, they use Pascal case for all method names. So capital S. I've got Java on the main, I've got Java on my mind. But that's another good example of something we have to pay attention to in every single language because it's spelled different. Sometimes it's all caps. Sometimes it's all lowercase. It's usually those 4 letters, just in slight variance. Somewhere I misspelled position over there. Come back over. Looks like hopefully the typos are fixing. It's taking longer to compile. That's usually a good sign that the typos are fixed. Right? You may have noticed that by now. When the compiler runs, error messages show up real quick. But when there's no error messages, it takes a lot longer. So we have that good sign. And I'm going to start by setting that threshold really high. So our dragon is at basically 0.30. And our knight is at 10.64. So I'm going to start by setting that threshold someplace pretty high. Let's try 20 and see where that gets us. Oh, yeah, that worked. So 20 is a pretty big threshold. So as soon as the game starts, we're within that threshold of 20. So it just rushes over and hits our character. We usually want to do that early check first. But now we can make that a more reasonable check. Let's see what 5 is. Now we hopefully have to get pretty close before the knight starts chasing our dragon. Okay, so he's still just kind of going in a big circle. Where'd he go? Oh, there he is. Five might be too close. If 5 might have been a little too close, so I guess that's one of the numbers we could have changed without stopping, huh? Let's see where 10 is. That looked like a better distance. If I can get my camera in a better spot, there we go. Just walking through his patrol. And we should see him turn and move towards the character at some point. Well, then it's just a matter of refining that last little number. Y'all can play around with that, right? When it was 20, The thing charged us as soon as the game started. This is another thing with the patterns. So as soon as the game starts, that character starts charging us. So we need to start moving away from it pretty quickly. And then it's walking around a different spot than it was earlier because it started running towards us and then stopped. There's someplace where I can see when it changes direction. Why isn't it changing direction now? I was definitely within 20 units there. Well, little glitches. We're very restricted on time. There's the general logic of what we want to do, what we want going on. Play around with those numbers. I wanted to leave most of the time to do that, but real quick, I'm going to make a duplicate of that. So I'll just hit Control C and Control B, the normal copy and paste, and move one over here somewhere. And give it a different name. Pheasant, that word goes go with that, and then maybe a different color. Create a new material. We've seen all this part before, right? Call it blue. Yeah, that would probably be better in the name. Because in something that has dragons and knights, we probably have a whole lot of peasants running around that would have like different things, different aspects. I couldn't think of a word very quick. I just wanted the third character in there. And then we can replace the material with the blue material. And the script, I want to remove that and add a new one specifically for this. So blue peasant. Yeah, make that script. And now when we open that one, oh, after compiler runs. A lot of it's going to be the same, so I'm going to start by copying everything from that night. Paste that in. So we'll still have our current position. This one probably doesn't need to go chasing our dragon now, right? Peasant or the NPCs can wait till our character gets to the NPC. If so, we don't need to go chasing it down. So this time we'll just start with our movement. I guess we don't really need to know where the dragon's at if we're not chasing it down. So we take this out. What I do want to do is, oh, and we don't need that distance threshold. That was for the enemy to attack, and you all will want to play around with that number. Find some good numbers to work in there. It should be a select structure. Just make sure you do that first. Check to see if you should be attacking. If you should be attacking before you go out, just do some random pattern. Something we'll need here, though, is some sort of value to tell us which direction to go in. I'm going to use an integer, private integer. direction. That sounds like a good name for it. And then what we want to do is set up our if else based off where that integer is. So I'll just kind of choose some number. Maybe this one's going to be going even slower. I'll choose some number, 450. Give it 550 seconds for the cycle. And choose some parts in there. So for like the first 220, and then 220 plus another 175. What's that get us up to? 395. So 220 plus 175 plus 85. Oh, we can do more than that. It's 395. So 115 would get us up to 410. And 410 plus 140 would get us back to that one, 550. So there's one extra number there, but again, it won't be destructive, and we would need little adjustments anyway, right from our starting point. But it adds up to that number. That way, every frame is pretty much accounted for. We have one extra frame. This frame start at 0, but I'm going to ignore that. And then this time we do need an else. So we're still doing the same thing. We're going to move in some direction. Actually, I'm going to abbreviate this one even shorter. That way it looks quite a bit different. So instead of making that exactly the same, let's say if frame mod 550 is not equal to 0, then we want to move in some direction, and otherwise we'll change our direction. I'm going to comment that out for a second, because if it's not that, then what we want to do is choose a direction. Yeah, that direction field, bless you. And range. That's the one I want. And then we can choose some number between 0 and 8. Well, 8 numbers, 1 through 8. And what I have in mind, try to draw this on the board quickly, because I was hoping to end about 10 minutes ago. That way there's lots of time to work on final projects. But we want to see the easy movement too. Random direction. I'm just going to do something like this. So we basically have 8 directions. So choose a number between 1 and 8, and whichever one it is, we can just give them numbers, right? 1, 2, 3, 4, 5, 6, 7, 8. And whichever one it is, we'll move in those directions. So random range, I remember what it is, but let's look it up. Random range unity. Oh, it's random dot range. I guess I typed random one too many times. The thing that's different time to time when we do a random range is notice that both of these are inclusive. So the number is included. So if we want number 1 through 8, we would put from 1 to 8. And it's random dot range, not range is Python. We don't need Python code here. So then we'll reset our direction, And what I like to do is always make sure this happens first. Because we didn't set one initially. So what I'm gonna do is start frame at too big of a number. Or, well, that's probably getting complicated. Let's just assign this. Yeah, probably easier just to assign this. So here, when we establish that, we can go ahead and assign it to some random number. And then we'll go 550 frames and pick another random number. And that's going to represent the direction we're heading off in. Then we need that selection structure like we had before. So like if direction is equal to 1, else if direction is equal to 2, else if direction is equal to 3. And has anybody worked with in a language that has switch case before? All of these are going to be exactly equal to. That's when we would want to use the switch case. And we are in the C family of languages. And so the switch case is definitely faster than the selection structure, than an if else. So a switch case would be faster, which is something we often want to take into consideration. But we haven't looked at that in this class, so I'm just gonna kind of skip that part. Just make a note of it for those who have seen that before. Kind of like that slight trigonometry note we needed earlier, that our simplified version was just a little bit off. 6, else if direction is equal to 7. And then there's only one left, so I'll just go ahead and do else here. And then we want to do all of this stuff. I'll copy that, paste that in here. I'm just gonna do plus speed each time. So if it's 1, we're going in the Z direction. If it's 2, we'll go in the well, I will go ahead and show this. Plus speed divided by, and let me point something on the board real quick again. We want to divide by the number, but we don't want a half, because the direction we want is like the hypotenuse of the right triangle. So we don't want to divide by a half. Those who have had trigonometry have encountered that if we go with a 45-degree angle, it's a real half. So we want to divide by math f dot square root of 2. Oh yeah, if we take 2 right triangles and put them next to each other, that's like a square, right? So the square root of 2 is the length, is the adjustment across there. It's not 2 on that adjustment. That would be a straight line. So to go with the angle, we need the square root of 2. In your trigonometry class, they probably wrote that rationalized. Square root of 2 over 2, but it's 1 over the square root of 2. Since the invention of calculators, there's not really any need to rationalize numbers. That's just how we split an angle in half. That's a 45-degree angle. For those who haven't had trigonometry, that number is going to seem kind of odd. Think about it like if we had 2 right triangles, we could put them together to make a box. And the angle going across that box, going across the square, it's not exactly half. Let's go with the square root of 2. It would take a lot to get into it. So then our next one would be a a vertical direction, or not vertical, vertical is the Y. We used Z the first time, so this time we need to do, what is that doing? That was weird. I pushed the tab key and bumped up something else at the same time, and it made a copy of that word. And then kept doing it. I'm not sure what the other key I pressed was. I could feel my hand hit something else. So the first time we moved in Z, so I'll cut that and move that over to the X here. Our angle's almost the same. Let me go back to the board. If I add some like those axes that we know from math class, then over here is a positive direction, and up here is a positive direction, and then these two are negative, right? So our angle 2 is both positive. 3 is going straight up, but 4 has one negative and one positive. So when we do that adjustment, instead of adding both of them, we'll need to make one negative and one positive. Then our angle 6, they're both negative. And then 8 is the opposite of 4, so we need to swap that positive and negative. Does that make sense? From math class, our positive and negative values. So when we go with this angle, over here we have a negative X using X and Y like math class. Negative X and positive Y. Down here we have negative X and negative Y. And over here we have positive X and negative Y value. So when we put that into our vectors, we need to adjust for that. So angle 4, I'll just put the negative sign first, and I'll copy that down to its opposite, which would be here, and swap that negative sign, swap that plus and minus so that we're going in the opposite direction. 5 is again completely vertical. So it's just like the first one where we went in the positive Z direction, except this time we want to go in the negative Z direction. So the exact opposite direction. And by now, hopefully y'all can see where this pattern's going, right? 6 is the opposite of that second one we put in, where those were both plus signs, and then that little adjustment to our speed, how much we want to move so that it's an even speed no matter whether we go horizontally or at an angle. We're going to keep that consistent, right? We don't walk faster just because we change direction slightly. If we're walking, we walk at our walking speed. Only this time they both need to be negative. So you just want to kind of set up your plot for which directions which, and choose which ones are going to be negative and which ones are going to be positive. Because they're vector quantities, so that negative does imply that. And then our other one is the opposite of when we moved in the X position or X direction. We just want to make it a negative speed instead of positive. So now it should just, the NPC should wander around in 4 different random things, and a collision would be about the same. I'll go ahead and set up a collision, might as well. Oh, we cannot initialize this here. That's what this error message is saying. We haven't seen that yet. It can't be called there, so it says call in awake or start instead. So I'll copy that and just make that in that declaration, and then in the start method, we'll go ahead and set the direction. Notice up here in C#, all we have is declarations. We don't have any assignments outside of that. That is a restriction we had not seen the error message from yet. Make sure that's saved. When we go back over here, it should compile. If we run it, we should be able to see that thing moving in random directions. Oh, well, there's no speed applied. First off, I'm going to change this number. Play around with numbers there and see if you can get that figured out. We are going to wrap up here very shortly. That chasing thing. And then here, I'll set the speed to like 0.05. That way that one moves slower than anything else in the game. And we can see it just wanders around in random directions. And like jumps through the ground and stuff. Oh, there it goes. And after a while, it changes directions and heads off in another direction. Which I'm pretty sure that just fell off the world. But the basic idea there is there. We don't have time to look at much other than the basic idea. So just choose a random direction and then an amount of time to go in that random direction. Would be the other main alternative to the bad. I'll do a quick collision. So instead of counting as an enemy, let's add another tag for NPC. So that one will get the NPC tag, and then back over in our dragon where we're handling all those collisions. Else if collision dot game object dot tag is. Oh, I'm not sharing my screen. How long has that not been shared? When did that screen share stop? Did we go over all the code? Okay. And then there was an error message for assigning it up here. We can't do assignments up here. Otherwise, it was just a test run if we looked at all the code. So back over here, switching that to give it a new tag for an NPC. And then just like we saw before in our Dragon script, we can check the collision, just see if we collided with an NPC. Oh no, I'll just debug.log. We're running very short on time. I'll just put a hello message to the console. There should probably be like a speech bubble that pops up at the minimum if it's not an audio track that plays automatically, but I wanted to finish 10 or 15 minutes ago. That way there's plenty of time to do stuff. Oh. Can't see the console if it's maximized. So over here, our blue guy is wandering off in random directions. I have no idea where it went. There he is. But I'm going to restart the game because I have no idea where that guy wandered off to. Check that collision. Okay, his speed might be a little bit fast. Oh. What was his speed? I'm not sure why he was outrunning me there. I don't think he should have been able to outrun me. There we go. And we get a little message pop up in the console. Don't have time to make a whole speech. You want to make sure there's plenty of time to actively do stuff. But that's the basic idea on player movement, or sorry, on the non-player movement. And see how it's a lot like what we did for the player movement, as long as we take into consideration when we decide to press those buttons. We have to decide when to change the movement, but then actually changing the move, making the new movement is straightforward. There's a couple versions of that. I will throw that up on GitHub shortly after class. Does anybody have any questions about those stuff from today? So some movement. Then Wednesday will be our last day of class, and we'll just kind of add things to this example for, I guess, about half of our scheduled time. And then there's still half of the scheduled time to work on projects and stuff. Because, yeah, we can barely scratch the surface of all the things in Unity. We'll at least see the basic components. If there's something you feel like you need for your game, your final project, send me a message or let me know, and I will plan to include that in our examples Wednesday, because it's just basically what we can fit in the last couple hours we have to talk. There's still a whole lot of stuff we can see in Unity. I have some things in mind, but if you have something in particular, I guess I'll take requests for the random odds and ends at the end. Otherwise, does anybody have any questions about the stuff from today? See, head checking no in here. I'll give it a couple seconds for people on the Zoom call. Okay, I assume 5 seconds of silence means no questions. If you have any, let me know. As always, I will be sitting around from now until our scheduled end of class at 4:50, ready to answer questions immediately. Text messages and every messages are the two things that make noise on my phone, so that's the quickest way to get a hold of me. Otherwise, I will see you all on Wednesday. Everybody have a great afternoon.